Hi, everybody. This is Mr. Folly. Oh, darn it, with the wrong pen. This is Mr. Folly, and welcome to 4B Lunch and 4A class. Say hi, class. All right, so we're going to roll through this and put some things down on paper from what we did from our ring of ping today. So, definitions you should know. Pressure is the force of a gas particle striking the container. Remember, the more pings you had, the more pressure you had. The units for pressure are atmospheres or kilopascals. And we do the annoying thing of making you convert all the time. So an atmosphere, one atmosphere is 101.3 kilopascals. Okay? We are supposed to use kilopascals in the metric system. One atmosphere makes so much more sense though. If you're at sea level, the air pressure is 1 atmosphere. Volume is the space a substance takes. Units are liters or milliliters. 1 liter is 1,000 milliliters. Okay? And that you should be comfortable with. Temperature is the average kinetic energy. Kinetic energy is motion, right? So temperature is average kinetic energy. The units are Kelvin, and you have Kelvin equals degrees Celsius plus 273. Get ready to be annoyed. I only ever give you Celsius. You're going to have to always add 273. Always add 273. Okay? And the reason why is if you're in any country other than America, the temperature they use is Celsius. So that's kind of where that little bit travels in there, and then we kick it into kelvins, okay? Now, average kinetic energy, remember, is the energy of motion. Remember how we promised bonus points to the kids that moved the fastest and they disappointed us all, right? That motion is what temperature is. That's how fast the particles move. The number of particles, the number of particles is N, and that's measured in moles. So there's one equation that we didn't talk about much. PV equals nRT. P is pressure, V is volume, N is moles, and then T is temperature. So we'll get to the R in a little bit. All right. All right, so now relationships between pressure, volume, temperature, and moles. Pressure is inversely proportional to volume. Inversely proportional means the graph looks like a Boyle. Remember how I talked about that? It's a big curve. Inversely proportional means one goes up, the other one goes down. We don't expect this. There aren't a ton of inverse relationships that we experience every day. Okay? And remember, so the equation's going to be laws, believe it or not, in science class are always equations. So this law is PV equals PV. And I'm going to put little numbers on it. P1, V1, beginning, P2, V2. The 1 means at time 1, and the 2 means at time 2. And then pressures in atmosphere or kilopascals and volumes in liters or milliliters. But they have to be the same. If it's volume, if it's milliliters on the left, it's got to be milliliters on the right. Okay. As pressure increases, volume decreases. That's the inverse relationship. Opposite, increase. Whoops. Decrease. Okay. If pressure is doubled, volume is halved. I'm saying this because the questions look like this sometimes. So you get used to the word halved, which I don't know if that's how you're really supposed to say it. Something's cut in half, but it's halved when you cut it in half, okay? A large balloon would have less pressure than a small balloon if temperature and number of moles are held constant. So this is pressure. Large balloon, big balloon, ping, ping, ping. Small balloon, shrink it down. So ping, 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 ping. Make sense? Good. And you do have to be able to identify whether it's inversely related or not based on the graph. Pressure is directly proportional to Kelvin temperature. That's Charles's law. P1 over T1 equals P2 over T2, where P is pressure in atmosphere. Yeah, it's the same unit things, right? As pressure increases, temperature increases. That's what it means to be directly proportional. Hey, up and up. If pressure is doubled, temperature is doubled. Now it's got to be Kelvin temperature is doubled, okay? Celsius temperature is not directly proportional, okay? So the temperatures in Celsius you should know is water freezes at 0. That's about it. Okay, water boils at 100. But if I go from 2 degrees Celsius, that means it's pretty cold, almost the temperature of freezing water. And I go to 4, that does not double the speed of the particles. Okay, that does not double the speed of the particles. That's why you can't use that. Okay. But if I have 275 Kelvin to 550 Kelvin, that's double. It does have double the kinetic energy. So the way we show energy is with arrows, like, oh, I made that arrow. I tried to do half as much and I just failed. So if I did this and I said this is half as much, see how this one would be moving twice as fast as that one. The other way we represent speed is if this is my particle, they do these things called whooshies. I think whooshies are dumb, but you'll see it a lot. So this one would be, whoa, look how fast that one's going, half as fast. It's just, you got to get used to them, okay? You didn't write down the whooshies? Write down the whooshies. And note, the dashed lines are projections. As real gases liquefy, this shouldn't be a surprise to you. Gases get really, really, really cold, they turn into liquids, right? At 0 Kelvin, the volume of a gas is 0. That means something has a volume of nothing. That doesn't make much sense. So that's why this is a theoretical number, right? So we can't really get to it. 0 Kelvin is called absolute zero. Someone knew that in class, and that's when we stopped. Okay. All right, here we go. All right, pressure is directly proportional to the number of particles, which is moles. So this is the equation for it. And, oops, where? And the same thing happens. If you double it, it doubles it. We did this just like the ring of ping. Cut it in half, cut it in half. Same, okay? If you blow into a balloon, so if I've got a balloon, oh, look at that, and I have, looks like 3 moles or 4 moles of particles in there. If I blow into the balloon and the balloon doesn't get any bigger, you can already feel there would be more pings in there, right? Pressure is going to go up. Why? Because it's got more gas particles in it, okay? All right. Pressure is directly proportional to the Kelvin temperature. Again, if the temperature goes up, particles move faster, you get more pings. So if you can think about this every time, pressure, pings, are directly proportional to Kelvin temperature. Temperature was moving fast, right? If you move faster, you get more pings. Think of your circle again, Kelvin, or the boom, 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 boom. If you're moving and you get ping, 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 but then you start moving, ping, 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 ping. Does that make sense? Increasing temperature increases pings. Okay. I think I grabbed a old one of this where it's got, as temperature doubles, the pressure doubles, et cetera, et cetera, et cetera. Okay. It looks like, I'm going to read this because I think I made a boo-boo. I grabbed my old draft of it. So pressure is directly proportional to temperature. So I think I accidentally have moles in here, right? So temperature, as the temperature increases, pressure increases. As Kelvin temperature doubles, pressure doubles. If moles are halved, that doesn't belong here right now, right? All right, does that kind of make sense? So now here's the demo where you'll see that. If you spray a can of compressed air, so you hit an air can, it goes tss. So if I said, oh no, there's a goblin in the corner, and we're all going to run, okay? And we're going to run out of the school as fast as we can because we know goblins eat sophomores, right? Who's going to get out of the school the fastest? Fast kids or slow kids? Fast kids, right? So the fastest particles leave, okay? So we say that the hottest particles leave first. If I have a balloon and there's a hole in the balloon, which particles leave first? The hot ones, right? So if I said, all right, every 5 minutes, the hottest people are going to leave this room, okay? So 5 minutes, the hottest half of the class leaves. Before too long, we're sitting here looking at me and Kellen, and that's it. And that's all over. Okay, does that make sense? So all the hot people left, and Kellen and I are looking at each other going, ping. So good. And then we look at the dashed line again. There's very low temperature gas liquefies, and all the stuff that comes about this. So you can read that. The last one, the ideal gas law, combines all the factors at once. It's PV equals nRT, and we talked about everything except for R. R is a constant that basically just makes our line go straight. So in math class, or it tells you the slope of the line. In math class, you have the number pi. And if I said, what's pi? You'd say 3.14159. Well, what is that? 3.14159. Pi is just something you throw into an equation to make it work, right? Circumference equals 2 pi r. What's pi? 3.1415. It's just a number that gets you the right answer, right? Does that make sense? What's the area of a circle? Area is pi r squared. What's pi? 3.14, believe it or not, if you graph these things, the slope of the line is pi. That's how that stuff's derived, which is kind of interesting, but you don't have to care about it. Multiple variables can be changed at once, so P, V, N, R, and T. You can change more than one, and you plug it in, and you'll get an answer for it. And that's it. So when we get back to class, we will be able to do some math, and that will work. So to that, I will say toodles. I hope you enjoyed it, because remember, without you, there is no us.